given time series has a unit root, and we saw that many macro time series do have unit roots. So then the question arises as to how we can study the relationships between unit root non-stationary variables. Okay, and that's an important question because most variables are unit root non-stationary. So the key idea is what happens when we combine unit root time series together. Okay, now most of the time you combine unit root time series, the series which has a unit root, which is also non-stationary. Okay, and if that is the case, then that means that there is no relationship between these two series. Okay, but there is a special case in which when we combine two or more unit root time series, that linear combination happens to be stationary. Okay, does not have a unit root. And that special case we call co-integration. And that is a very important idea in economics, because the only way two unit root processes could have any relationship with each other is if they are co-integrated. Okay? Unit root means the variable will be very volatile and it could go anywhere. Okay? So if we have two unit root variables, they are both very volatile and they could both go anywhere. Okay? The only way they could have a stable relationship or an equilibrium relationship is if their combination does not have a unit root. If their combination does not have a unit root, it means individually the variables could go anywhere, but that combination will remain stable, will remain stationary. So that combination can be interpreted as an economic equilibrium. Okay? So that's the intuition behind it. Now we will look at this idea in more detail. Okay? So last time we started this. So suppose we start with two unit root variables, x1 and x2. Any unit root variable we can always decompose in this form. It must have a stochastic trend, which is the sum of all the past shocks, because each shock is permanent, so they keep on getting added up. That we call a stochastic trend. So x1 has a stochastic trend, x2 has a stochastic trend. That is necessary part of any unit root process. Okay? Now, in addition to the stochastic trend, it could have any stationary part in it. Okay? And so that's the second part. And then the third part is just an initial value, starting value. x1 at time 0, x2 at time 0. That's just some constant value. Okay? Okay. Now we want to analyze the behavior of a combination of x1 and x2. So we look at a vector beta of weights 1 and minus beta 2. Okay? So the weight of x1 has been normalized to 1. Okay? And the weight of x2 is minus beta 2. Why do we have a negative number for the weight? The reason for that is, so xt is x1t, x2t. Now we're going to form a linear combination zt. So zt is beta prime xt. So now this is going to be x1t minus beta 2 x2t. Okay? So the reason why we have a negative number here and why we want to normalize this by 1 is as follows. We can think of doing a regression of x1 on x2. So you add some, maybe a constant and an error term. So if we write the vector in this way, then we can have a regression interpretation of this linear combination. So if we were to do a regression of x1 on x2, then x1 would be some constant plus beta 2 x2 plus a random error term. So when you bring x2 to the left-hand side, it becomes x1 minus beta 2 x2t. Okay? So the reason we write it in this way is because in the back of our mind, we have this regression interpretation. Okay? That's how we estimate the beta. We will do some kind of a regression to estimate the beta. So the coefficient on the left-hand side, well, that's its weight is naturally going to be 1. And the one on the right-hand side, it's when you bring it to the left-hand side, it becomes minus beta 2. Okay, so when we write this linear combination, then what are we going to get? Well, we know x1 has a stochastic trend, and then beta 2 times x2t. x2 also has a stochastic trend. Both x1 and x2 have a stationary part. So when you combine two stationary parts, you get something else which is stationary. And both of them have an initial value. If you combine them, you still have another initial value for zt. So then zt has these two stochastic trends plus a stationary part plus an initial value. So zt has a stochastic trend or a random walk component, which is this. You can combine it together. Now, in most cases, zt will also be I1. It will have a unit root. And this result that if you combine I1 variables, you will in general get something which is I1. Okay? So that's a general result. If you combine I2 variables, in general you will get something which is I2 also. Okay? Most of the time. But an exception from this result is if there exists a vector beta so that the linear combination zt is a stationary process. So this vector beta may not always exist, but when it exists, we call it a co-integration vector. And what co-integration requires is that the stochastic trend in x1 cancels out the stochastic trend in x2. Okay? So the two stochastic trends are basically the same, they just differ by a constant. So the stochastic trends are proportional to each other, so when you form a linear combination with the correct weights, they will cancel out and you will end up with something which is purely stationary. Okay, so we say that the variables x1 and x2 share a common stochastic trend. Okay, they share a common stochastic trend. Now, to obtain co-integration, there has to be fewer stochastic trends than there are variables in xt. What does that mean? So here in xt, we have two variables, x1 and x2. So if there are two stochastic trends, then there is no cointegration between x1 and x2. Cointegration means that there is only one stochastic trend. And so both x1 and x2, they share this stochastic trend. So with two variables, to obtain cointegration, there should be only one stochastic trend. With 10 variables, there can be at most 9 stochastic trends to obtain cointegration. So for n variables, you can have at most n minus 1 stochastic trends. Fewer stochastic trends than there are variables in xt. Now, if we consider a regression type of formulation, so x1 is mu plus beta 2 x2. So we can think of mu as the mean of this linear combination zt. Ut is a zero mean error term, and it is stationary. If x1 and x2 are cointegrated, then this u has to be stationary. Now, the other thing to note is that if there is one cointegration vector, then there are infinitely many cointegration vectors. So the cointegration vector is not unique. So if there is one cointegration vector, 1 minus beta 2, if you multiply this with any constant number b not equal to 0, that will give you another cointegration vector. Okay? And the reason for that is, what's the reason for that? If this is a cointegration vector, if you multiply this with a constant, you get another cointegration vector. Why? Why is that?
Because x1 is normalized to 1, and you can normalize it to another number.
Yeah, you can normalize it to another number. That's, yeah. So the idea is zt is beta prime xt. This is stationary. So if I multiply zt by 2 times, if zt is stationary, 2 times zt is also going to be stationary. 10 times zt is also going to be stationary. So if zt is stationary, that means beta is a cointegration vector. Then if I multiply that by any other constant, that will still be stationary. Okay? So therefore, you can multiply the cointegration vector by any constant, and that still gives you a cointegration vector. The only difference is here we have imposed a normalization on the first coefficient. Okay? And this normalization is natural and intuitive because we have in mind a regression formulation. Okay? But you could choose any other normalization that you like. Mathematically, it's exactly the same thing. Is it clear? Okay, so cointegration closely related to the concept of economic equilibrium. We, right from the first day we start learning economics, equilibrium is the main concept that we look at, right? Supply, demand, intersection, equilibrium. If there is a demand shock, the demand curve shifts, you move to a new equilibrium. But has anyone ever seen an equilibrium? Okay? How can you identify what an equilibrium is? It's a very deep question, right? To talk about it theoretically, to draw pictures and move curves, that's one thing. But in reality, do we see equilibrium? Can we measure the equilibrium quantities of these non-stationary variables? Okay, so for doing all that, co-integration tells us the answer is yes. We can measure the equilibrium quantities of variables, and that's what we will learn how to do. Okay? So original variables x1, x2, they are non-stationary. So shocks have permanent effects on the levels of these variables. And co-integration says, however, that the residual ut, okay, that is the deviation. So if x1 and x2 are co-integrated, that means ut is stationary. And ut represents a deviation from this equilibrium relationship between x1 and x2. Okay? So that is like a deviation from the error term. Now co-integration is telling us that ut is a stationary process. So that means shocks have only transitory effects on ut. So what that means is x1, x2 individually, shocks to them are permanent, but shocks to the linear combination between them, they are stationary. So if there is a deviation from this linear relationship, that deviation cannot last for too long and it will ultimately die out. Okay? So that's why we think of this relationship as defining an economic equilibrium. So x1, x2 themselves can wander arbitrarily far up and down, but they never deviate too much from equilibrium. We can even measure the equilibrium value of x1. We call it x1 star mu plus beta 2 x2. There's no error term here. So if there is the error ut is 0, then x1 is at its equilibrium value. And so we think of x1 star as the equilibrium value of x1, and ut is the deviation between the actual value that we observe. So x1 is the observed value, x1 star is the equilibrium value. So equilibrium value is the value at which there is no tendency for x1 to move away. Right? So equilibrium means you have stability, you've reached some kind of stable value and you're not going to move away from that. But because the economy is continuously being hit by various kinds of shocks, preference shocks, supply shocks, fiscal and monetary policy shocks, so the system will never settle down at x1 star t, never settle down at the equilibrium value. So x1 will not converge to x1 star t in any sense. Right? But the deviation between x1 and x1 star will be stationary. Okay, that's what we can say. Now, we can generalize the notion of co-integration to more than two variables. So now, let us suppose we have a p-dimensional vector of variables, x1, x2 through xp. And then we define a normalized co-integration vector beta. The first one is normalized to 1 and minus beta 2 up to minus beta p. This is a co-integration vector if beta prime xt, which is this, is a stationary process, I0 process. So exactly the same idea. But now, with p I1 variables, there can be several different co-integration vectors. So the more variables you have, the more possibilities for more than one co-integration vector. Okay? But with p variables, okay, there can be at most p minus 1 co-integration vectors. Okay? Theoretically, this is not a problem, but the tools that we will look at here, they assume, for simplicity, a single cointegration vector. In practice, I will show you how to estimate multiple cointegration vectors as well. Okay, now let us see how this concept of cointegration is useful in economic models. Okay, so the first example we look at is the most famous theory of exchange rates, which is PPP, purchasing power parity theory. So suppose x1 is the log of the nominal exchange rate, bilateral exchange rate between the dollar and euro. It's denominated as dollars per euro. So what is this exchange rate now between euro and dollar? Does anyone know? How many dollars per euro? $1.12. Yeah, that's close enough. Okay. Yeah, around 1.14 or 1.15, somewhere there. So that's the nominal exchange rate. And so what does PPP say? So we have this nominal exchange rate. This is in dollars per euro. Say currently about this much. Okay? So PPP says that this nominal exchange rate should equal what? Yeah, it should equal the price level of the US, which is in dollar terms, over the price level of the euro So this is what PPP says. Okay, we'll understand the meaning of this more clearly later on. So in log terms, we have something like this. So let's call this x1 t, call this x2 t. Then zt, well, so if these two are equal, okay, these two are equal according to PPP. So if we form a linear combination, this linear combination should be I0 if PPP holds. So if PPP holds, PPP is saying x1 and x2 should be the same. So what linear combination should we look at? Well, we just look at their difference. According to PPP, the difference should be 0. Okay, 0, of course, is very strong. It's a constant. So it is definitely stationary. Okay, so x1 and x2, individually, the nominal exchange rate and these relative price levels, they have a unit root, but their difference should be 0 or stationary. Okay, then that means what is the cointegration vector here? So it means x1 and x2 are cointegrated with a cointegration vector beta prime equal to 1 and minus 1. Okay, 1 and minus 1. So that's the cointegration vector here. Okay. Is it clear? Okay. Okay, so for most countries, consumer prices and exchange rates, they are non-stationary. And if the deviation from PPP, if this deviation is stationary, we can think of PPP as a valid equilibrium relationship between US and Euro area in this case. So this would be 1 minus 1 would be the co-integrating vector. And on the other hand, if this linear combination is non-stationary, that means they are not co-integrated, so the price differential can wander arbitrarily far from the PPP value, so there is no equilibrium interpretation of PPP. Okay, some more examples. Prices on the orange market. So we look at figure 1A, which shows us the price of organic and regular oranges. This is organic, this is regular, in pence per pounds. And graph B illustrates the price differential between the two. So the red is the organic, blue is regular. Okay? Are they stationary or non-stationary? These variables are the prices. Do they look stationary or non-stationary? Non-stationary, right? But they could be trend stationary, right? May not necessarily have a unit root. We could test that later on. Now, the other thing to note is the organic seems to be more volatile compared to the regular one, but they seem to move together very closely to each other, right? So it seems they share some trend. Could be a time trend that they share, or it could be a stochastic trend that they share, but seem to be moving together very closely indeed. If you look at the price differential, this difference, does it look stationary or non-stationary? Looks quite stationary, right? Mean value maybe somewhere around 20 cents, right? Sometimes up, sometimes down, but it converges to its mean value pretty sharply whenever there is a deviation. So the price differential seems to look relatively stationary. So that tells us, well, maybe these two might be co-integrated with each other. Okay. So the individual prices are obviously non-stationary, and a possible interpretation is that the non-stationarity is because of the unit root or stochastic trend. The prices show strong co-movements, however, and the price differential looks much more stable and could be a sample from a stationary process. So that suggests that we could construct a model for the organic oranges, as a constant plus the price of the regular oranges plus an error term. That defines an equilibrium for the orange market. And you would expect organic oranges to be more expensive than the regular oranges. So you add this constant mu, the additional price, and ut would be a deviation from the equilibrium at time t. Okay? So the differential will not equal mu in any specific period, but it won't go far away from that. It just means that fluctuations in the price differential around mu will be stationary. That's what the second graph shows us. Now we next look at private consumption